Hello. In this video lecture, I will be covering Module 8 and Chapter 8, and the subject of the chapter is momentum, specifically what we call linear momentum. I'm going to talk a little bit about it, and the chapter is a little bit large. However, I will be skipping certain parts of the chapter. I will let you know about them as we go along, but let's talk about what is momentum. Simply speaking, the concept of momentum, or the definition of momentum, is basically the product of the mass of the object times its speed or velocity. The symbol of momentum is the small letter p, and so it is equal to the mass times the velocity. Okay? Now, since velocity is a vector quantity, therefore the momentum is also a vector quantity. Okay? Now, what does that mean? What momentum means? Let me give it to you in an example. Imagine you have a brick wall. Okay, so there's a brick wall here, and you and I are standing, let's say, a few feet away from it. Let me finish drawing it. All the bricks here. There it is, something like that. Okay, let's say you and I are standing somewhere here, and let's say you are holding a gun. All right, and the gun has a 22 millimeter bullet. Okay, well, that's about the size of a cigarette filter. Okay, and on the other hand, I am holding in my hand, or on the floor, on the ground, a big boulder. Okay, a big giant boulder, but I am strong enough to carry it and hold it with my arms above my head. Okay, now both of us almost at the same time, you pull the trigger, you shoot the bullet toward the wall. Okay, so it hits the wall somewhere here. Me, I grab the boulder, I lift it above my head, and then I throw it as hard as I can toward the same brick wall, and it's going to hit it somewhere here, for example. Okay, the question is, which one will make more damage? The bullet or the boulder? Now, from my experience asking this question to students in class, say 100 students in the class, usually I would say about 50-50. 50% of the students are going to say the bullet, the other ones will say the boulder. And each of them have their own argument about it. And that's pretty good, actually. To be honest, if you ask me what is the answer, I don't know until we actually do the experiment and find out which one will make more damage. But both answers are kind of correct. Here is why. Those who say that the bullet will make more damage, because they are thinking about the speed. The bullet, the speed of a 22 millimeter bullets, it's something, I don't know, maybe Mach 1, maybe the speed of sound, roughly 350 meters per second. So it's an extremely fast object going toward the wall. The boulder, on the other hand, it's very slow, especially given that I'm the one who's throwing it. It's extremely slow, maybe 1 or 2 meters per second, not 350 meters per second, but it is massive. Okay, so those who say the boulder because they're thinking about the massive boulder. Those who say the bullet because they're thinking about not the mass, but they're thinking about the speed itself. So which one will make more damage? Well, as you can see, maybe you have answered the question already. And that is, it's really this combination of mass and speed. Imagine if you combine them together. In other words, imagine a boulder at the speed of a bullet. Now look at that damage. The damage is going to be, basically the boulder probably just going to go through the wall. You see what I'm saying? So this is what we mean by when we say momentum. It is this fatal combination of mass and speed. Okay? So when you combine them together, it gives you that collisional power of an object. Okay? The collisional strength of an object. Think of it like a football player, a big guy as big as a refrigerator. He is running as fast as he can, hitting smaller guys there. Why? Because he has very, very large momentum. Or think of a big semi-truck going 65 miles an hour. Very massive truck going very fast. So you can imagine the you know, God forbid, the collisional power of that thing, and so on, okay? So when we think of momentum, the first thing that comes to your mind, at least to my mind, collision, okay? Because the larger the mass and the larger the velocity, you get more momentum, okay? Okay, so that's basically what momentum is, collision. We're going to be studying, so the whole chapter in here is all about collision, and we will be talking, we will be doing a lot of problems that have to do with that. Okay, I'm going through the book here. Now I want to talk about conservation of momentum. Okay, I hope you will take the time to read the entire chapter before you watch this video, because it's just like I said, the chapter is very long. It's about looking at almost 30 pages long, and it's just there is no way that I could do it in an hour and a half or so. So please take the time to read the chapter. I'm just going to be kind of picking and choosing certain topics, but the concentration of this video lecture is going to be on working out examples and problems. Okay, now we come to what we call conservation of momentum. Conservation of momentum. Just like we studied before the conservation of energy, remember that? And we said that energy, the total energy, E, is the sum of the kinetic plus the potential, and that sum is always constant. Remember that? We talked about all of that. So we have a similar concept for conservation of momentum. So I'm going to explain it to you in an example, okay? Here is how it works. Imagine you have 2 billiard balls, okay? So here is the floor or the pool table, and I have 2 balls here. I'm going to call it ball 1 and ball 2, like that. So this is ball 1, this is ball 2. Now let's suppose that both of them are moving towards each other like that in a collision course, okay? So I'm going to call this V01, which means the velocity of ball 1 before collision. The naught here means before collision. Keep that in mind, okay? So slightly different from what we've done in kinematics. So V, the naught, means before collision. And then I have V02. And of course, ball 1 and ball 2 have different masses, assuming that. So M1 and M2, okay? I'm going to call this BC, okay? These are my own terminology. BC for before collision, AC after collision, and DC during collision. We're going to cover those 3 abbreviations later in the video. So this is BC, before collision. So you get those 2 billiard balls. Each of them has different speed, not necessarily equal. Have different masses, not necessarily equal, and they're about to collide with each other, okay? So what happened? They will collide, and then they will rebound in the opposite direction. So AC is going to look something like that. I'm going to draw it here. Let me erase that. So here is ball 1 now rebounding like that, and then here is ball 2 rebounding in the opposite direction. And I'm going to call it, see, there is no naught there, it's just V1 and V2, you know, which means after collision. You got that? I can put prime, which means after collision as well. I may use that later. But if I don't put the naught here, this naught, it means after collision. You got it? So I'm going to call this AC here. Maybe I'll put it here. Okay, so that's what's happened. Of course, nothing happens to the masses. There's no loss or gain of the masses. All right. Now, here's what I want to do. What is the momentum of the 2 balls before collision? Remember, we said momentum is equal to what? MV, okay? It's MV. So what's the momentum of the 2 balls before collision? Well, the momentum of ball 1, and remember, momentum is a vector, so you really want to take care of direction. Remember, direction is very important. So if it's going to the left, it's negative. If it's going to the right, it's positive. If it's going up, it's positive. If it's going down, it's negative, and so on. Okay. So, all right. So, what is the momentum of ball 1 before collision? Well, that's going to be, I'm going to call it, say, P1, or P01 rather, and that's equal to M1 V01. Correct? And of course, it's going to the right. That makes it plus. Now, the momentum of ball 2 before collision is going to be minus m2 v0 2. Okay? Now, after collision, so what is the momentum of ball 1 after collision? And that's going to be P1 is equal to minus m1 v1, and the momentum of ball 2 after collision, and that's going to be m2 v2. Okay? Here is the thing. If I would add up, okay, if I would take those two momenta, okay, those two momenta before collision, momentum of ball 1 and ball 2, and if I would add them up together like this, add them. In other words, I'm going to get something like this: m1 v0 1 minus m2 v0 2, and I get some number out of it, okay? And I'm going to do the same thing here for after collision, minus m1 v1 plus m2 v2. Well, I will find out that will always be that those two sums are equal. Can you believe that? Okay? In other words, the sum of the momenta before collision is equal to the sum of the momenta after collision. I have a symbol for it. I just say sigma p naught is equal to sigma p, or p prime, after collision. This is the statement of the conservation of momentum. Okay? This is very, very important mathematical statement here. What is, when we say conservation of momentum, what does that mean? It means the sum of the momenta before equal to the sum of the momenta after. That's it. Nothing more, nothing less. You got it? Okay. And we can use this to, solve problems and so on. I'll come back to the conservation of momentum. But let me do a couple of problems. Let's look at example 8.4, page 226. Right, I'm going to do example 3 in a minute. Let me do 4 first. So what we have in here, right there, he says two gliders move toward each other, and the figure is next page, unfortunately. Here it is. Let me show it to you very quickly. Right here. Okay, so we have an air track. Do you see this thing, those with holes? That's an air track. And these are two gliders that sit on the air track. They're both moving in opposite direction initially, BC, before collision. Glider A, glider B. Glider A is 0.5 kilogram. Glider B is 0.3 kilogram. And before collision, look at the symbolism he uses. It's a little bit different from mine. So anyway, so the initial velocity of B is 2 meters per second. And the initial velocity of, did I say A? I meant. And the initial velocity of B is negative 2 meters per second. Okay? So what happens, this is before collision. And then after collision, right here, they rebound in opposite direction, as you can see. And now he says that glider B is going with 2 meters per second. Remember, it started with negative 2, and it's also, so it kind of retained the same speed. Now he's asking the question, what is the velocity of glider, the final velocity of glider A? Got it? So that's what we're going to be solving. So let me go back to the problem again. So he said two gliders move toward each other, which is assumed frictionless, glider A math, Okay, so basically that's what he's saying, what I have just explained to you. So let's work on this problem. Let me just take the data. .4. Luckily, I have my hard copy here, so I can write down all the answers, all the not the data that we have. Anyway, so the picture looks something like that. Here is glider A moving with V0 A, let's call it. And then here is glider B moving with V0 B, and this is BC, right? And then AC, we have A moving in the opposite direction like that. I'm going to call it V sub A. And glider B is also moving in the opposite direction. But okay, so he gives you the speed of B, and that is 2 meters per second. And the initial velocity of glider B is -2. As you know, y is negative because it's moving to the left, correct? And then glider A, the initial velocity is 2 meters per second, okay? And he gives you the masses. The mass of A is 0.5 kilogram. Sorry for the clutter. And then the mass of B is equal to 0.3 kilogram, okay? There we go. And now he wants, what is the speed of glider A after collision? Got it? So what I want to do, I want to use the conservation of energy, the conservation of momentum to solve this problem. So what does the conservation of momentum say? Let me write it down again. It says sigma P naught equals sigma P. The sum of the momenta before equal to the sum of momenta after. So let me write them down. And now I'm going to write down those equations, but also while looking at this picture and putting the signs of the velocities, minus or plus. You see what I'm saying? So let me look at BC first, right here. So that looks like to me like this: M sub A, V naught sub A, minus M sub B, V naught sub B, equals to, this is all before, after, minus M sub A, V sub A, plus M sub B, V sub B. Got it? You see what I've done? Okay. Remember, I'm solving for V sub A. So the next step, I can just plug in the numbers and be over with, and then just solve for V sub A. So M sub A is 0.5 times V naught sub A is 2 minus M sub B is 0.3 times V naught A is what? 2. I already took care of the minus sign. Be careful, okay? So he is ahead of me by putting it minus. He shouldn't have put minus, really, but he's a little bit ahead of me. But this minus is the same as this minus, so you don't want to do it twice. So it's basically 2 equals to minus M sub A. M sub A is 0.5, we said. V sub A is still unknown to us, plus M sub B is 0.3 times V sub B is 2. And there we go. The rest is really easy. So now I have 0.5 times 2 is 1. This is minus 0.6 equals to minus 0.5 V sub A plus 0.6. So I have 1 minus 0.6 minus 0.6 equals minus 0.5 V sub A. I hope you're following my algebra. And that will be 1 minus 1.2 equals minus 0.5 V sub A. And that will give me negative 0.2 equals negative 0.5 V sub A. The minuses cancel out, so V sub A is equal to 0.2 over 0.5. What is that? I don't know. I need to look it up. Calculator. So I have here 0.2 divided by 0.5. And that's equal to 0.4. It's 0.4. So V sub A is equal to 0.4 meter per second. You see what I'm saying? That would be the magnitude. Remember, we already took care of the sign of V sub A right here. You see what I'm saying? So this is the magnitude of it. And the direction, of course, to the left. I already took care of that here. You see what I'm saying? Now, you could have chosen not to put the minus sign, and then the answer would have been minus automatically. But anyway, there we go. That's how you do it. Okay so far? Okay, good. Let's do one more. I want to do example 8, the one previous to it. 8.3. 8.3. That's a recoil of a rifle, it says. Let me go back to the book. There we go. Okay. You know, I don't know how many of you have ever shot, used the rifle and shot through it, but if you would use the rifle and then pull the trigger, the rifle will recoil and hit your shoulder. You see what I'm saying? As the bullet come out. Okay, the question is, what is the which one is faster, the speed of the bullet or the speed of the recoil of the rifle? Let's read this example. And this is a classic example of momentum conservation. We will see why a rifle recoils when it is fired. Okay? A marksman holds 3 kilogram rifle loosely. Okay, so we have a rifle, 3 kilogram, so that we can ignore the horizontal external forces acting on the rifle bullets. Okay, he fires a bullet of mass 5 gram horizontally with a speed of 300 meters per second. Okay, that's about the speed of sound. So that's Mach 1. Got it? What is the recoil speed of the rifle? Okay, what are the final kinetic energy of the bullet and the rifle? Okay, we'll talk about the kinetic energy in a minute. Do you think the speed of the rifle recoiling back is equal to the speed of the bullet? I hope you don't think so, because you're not going to get a speed of the rifle is going to recoil against your shoulder with Mach 1, 300 meters per second. Okay, that will be fatal, basically. So it's going to recoil, but it will with a certain speed. Okay. The question is, before we know what the speed is what's being equal here? Okay, what is being equal? Let me explain. Let me draw a rifle. So here is a rifle. All right. And here is the bullet lodged in there. Okay, there is the bullet right here. Okay. Now, you fire the trigger, and what's going to happen? The rifle going to rebound back with some velocity. Let's call the rifle 1 and the bullet 2. Is that okay? So it's going to recoil with some velocity v1 as the bullet shoots out with velocity v2. Okay? So far so good? Okay. Now, I'm going to use conservation of momentum. We said that the sum of the momenta before equal to the sum of the momenta after. Okay? Now let's ask the question. Remember, this is before. This is BC, not BC, BC, and this is AC, even though there is no collision here, really. Before firing and after firing, if you will. Okay? But so I'm going to still call them BC and AC. Look at BC here. What is the speed of the bullet? 0. It's just sitting there. I didn't pull the trigger yet, right? What's the speed of the rifle? 0. So basically, sigma F here is really 0. In other words, I mean, I can go, let's assume the mass of the rifle is big M. And let's assume the mass of the bullet is small m. Okay? So in this case, if I'm going to write down what is sigma P naught, it's just going to be big M V1, V naught 1 plus small m V naught 2. Correct? That's BC. But as you can see here, the bullet and the rifle are at rest. I haven't pulled the trigger yet. So this is 0, this 0. What I'm trying to say is that the left-hand side of this equation is 0. Equals to. Now let's look at after collision. What's going on here? Well, the rifle is going to go to the left. The bullet's going to go to the right. Right? Assuming this is left and this is right. So that's going to be big M for the rifle, V1 with a minus, plus small m V2 for the bullet. See what I'm saying? And then all I need to do is, let's say I move the momentum of the rifle to the other side. So I have big M V1 equals M V2. Therefore, V1, the velocity or the recoil velocity of the rifle, is small m over big M V2. That's it. I'm done with it. So therefore, V1 is the mass of the bullet, which he said, I'm looking at my hard copy, 3 grams, 3 times 10 to the negative 3 kilogram, divided by the mass of the rifle. He said it is, I'm sorry, I made a mistake. I read the wrong thing. The mass of the bullet is 5 grams, so that makes it 5 times 10 to the negative 3 kilogram, divided by the mass of the rifle, 3 kilogram. Multiply this by V2, and V2 he said 300. And all we need to do is just you work it out. So we have here 5 negative 3 divided by 3 times 300. Answer half, or yeah, 0.5 meter per second. As you can see, it's extremely slow compared to the compared to the velocity of the bullet. Why is that? Why is that? The reason is because the rifle is extremely massive. If they were both of the same mass, they would actually move, or the rifle would recoil with exactly the same mass, same velocity as the bullet. You see what I'm saying? But because this is extremely massive, so the speed is much slower. You got it? Okay. The second part of the problem says, what are the final kinetic energies of the bullet and the rifle? Okay. All you need to do is just to kind of calculate the kinetic energy. K for the bullet is 1/2 mv squared. Just calculate it. So 1/2. The bullet says 5 grams times 10 to the negative 3 times the velocity. We found it to be 300 squared, and we can calculate that. I'm just going to get the answer from the book. It's 225 joule, and then the kinetic energy of the rifle, and that's 1/2 big M V. I'm sorry, this is V2 and this is V1, right? So that would be 1/2 times the mass of the rifle, 3 kilogram, times the velocity of the rifle is 0.5 quantity squared, and you calculate that, and it turned out to be really tiny, 0.375 joule. As you can see, the kinetic energy of the rifle is extremely small compared to the kinetic energy of the bullet. It is the bullet that takes all the kinetic energy from that, when you shoot it. Okay, good. One more example that is a little bit harder, and that is in 2 dimensions. So let me go over that. And that is example 8.5, collision in a horizontal plane, basically 2 dimensions. And in such case, you're going to be doing, X and Y component. It's a little bit harder. Let me go over that. Example 8.5. Okay, let's go to the book. That's in next page, should be. Here it is. Okay, so what you have, as you can see here, you have 2 objects. One is moving, one is stationary. They collide. Object A move in this direction, object B go in this direction. As you can see, you have 2 angles of scatter. We call it angle of scatter, and he's asked to do something. Let's see. Now we will have to keep track of book. He talks a lot. What is the problem here? Okay, he says chunk A. Okay, this is a chunk of ice. Chunk A with mass 5 kilogram moves with initial velocity 2 meters per second, parallel to the x-axis. Okay, horizontally to the right. It collides with chunk B, which has a mass of 3 kilogram. Okay, so it's a little bit lighter, and is initially at rest. Okay, after collision, the velocity of A is found to be 1. So after collision, the velocity of A right here is 1, and in the direction, in a direction at an angle alpha is 30 degrees right there. Got it? Okay. So then he asking a question: what is the final velocity of B, chunk B, and the direction and the angle beta? Okay? All right. How do we do this problem? Pay attention, because you're going to break it into components, X and Y component. Okay? This is a 2-dimensional problem. Okay? So let me draw it first. So what you have in here, in the beginning, so we got BC and AC. So we have chunk A here moving. Here is chunk B. And this is V naught A is equal to 2 meters per second. And the mass of MA is 5 kilograms. And then chunk B is at rest initially, right? So V naught B is 0, and the mass of B is equal to 3 kilograms, right? This is all BC, okay? That's BC. Now AC, I'm going to put it here on the same direction, the same line. So here here is chunk A moving like that. I'm going to call it V sub A, and it is moving with a speed of 1 meter per second. And then you have chunk B right here moving V sub B with a speed unknown, angle beta, and this is angle alpha equals to 30 degrees. Okay, there we go. Now he's asking, what is V sub B and the angle beta? This is AC, of course. Oops, sorry, 1 second. Okay, so how do we do this problem? Well, exactly the same technique that we have been following, and that's basically what you do is you use the conservation of momentum. Okay, so sigma P naught equals sigma P. However, since I have 2 dimensions here, okay, x and y, so I'm gonna break this equation right here. You can think of it like a vector equation as this: sigma P naught in the x direction equals sigma P in the y direction, and then sigma P naught in the y direction. I'm sorry, go back to this one. Sigma P naught in the x direction equals sigma P in the x direction after collision. That's what I wanted to say. And then sigma P naught in the y direction equal to sigma P in the y direction after collision. Got it? Okay. But before I do that, I need to resolve things into components. As you can see, looking at BC here before the collision, everything is along the x-axis, no problem. So here you have the initial velocity V naught A is basically along the x-axis. There is no y component. You agree with me on that? And of course, this one is at rest B, so there is no y or x component for that matter. The troublemaker is after the collision. So I need to resolve VA into VAX and VAY, and also VBX and VBY. Got it? So I need to do all of that before I plug it in. So here's what's going to happen here. So let me just talk about AC here, because AB is fine. So as you can see here, VA sub Y, that's going to be VA sine 30, and that makes it 0.5 VA. VA, remember, is 1. And then VA sub X, that's going to be VA cosine 30, and that makes it 0.866 VA. Is that okay? All right, and then for B, I hope you're taking notes. It kind of disappeared from the screen. VB sub X is going to be what? Here it is. VB sub X is going to be VB cosine beta, correct? That's going to be VB cosine beta, and I don't know either of them. I'm just going to leave it like that. And then VB sub Y, well, guess what? It's going to be negative, right? Because VB sub Y is going to be this way, and that's going to be negative minus VB sine beta. Okay, there we go. So these are the components. Now let me go and apply conservation of momentum. Sigma P naught X equals sigma PX after collision. Sigma P naught Y before equals sigma PY after. Got it? Let's do it one by one. So let's start with this one. So here, well, while looking at the picture, so that's going to be, I am going to be starting with this one. So I'm going to start with A, and that's going to be, remember, momentum is MV. So that's going to be M sub A. Let me put it in symbols first. MA V naught A plus what? MB times 0, right? It's at rest. Equals to, now let's start with this one. In the x direction, here they are, guys, right here. These are the ones in the x direction. So I'm going to go with MA, VA in the x direction, which is right this one, times 0.866 VA plus, and then Vx is going to be plus, sorry, I'm running out of space, plus momentum x for the B, and that's going to be m sub B, m sub B, and then VB cosine beta. There we go. I have that. Okay? I'll come back to it in a minute. Let me do the Vy then here. So I got that. Now let's do the Vy. So it's going to be, well, this is the easy part, the left hand. What are there any y component before collision? The answer is no. So this whole thing is 0. Zero. What an ugly looking 0. There we go. 0 equals to. Now, P sub y, that's going to be MA VA 0.5 VA, right? Sorry. I'm copying this one. I'm copying this one, guys, right here. So that's MA 0.5 VA minus this one. MB times the minus here, I'm going to have VB sine beta. There we go. Okay. Now, what's cool about this equation is remember, I know VA already, so I can get a lot of information out of this one. So let me move this part right here to the other side, and that's going to be MA times 0.5 VA equals to MB VB sine beta. Now put in your numbers. MA is equal to, again, I'm looking at my my book here. MA is equal to 5 times 0.5 times the velocity of A after is 1 equals to MB is equal to 3. VB I don't know, sine beta I don't know. I have that, okay? So I can do it in one shot with this equation. I can say that V sub B sine beta is equal to, all I need to do is multiply 5 times 0.5 divided by 3. So 5 times 0.5 divided by 3, and so, whoops, I need to do it again, darn it. What is it? 5 times 0.5 divided by 3, answer 0.83. So I have here 0.83. I hope I didn't make any mistakes. So I got this equation. Let me box it and I'll come back to it. I'm going to call it equation 1. I'll come back to it. Now I need to work on the x component, which is right this one right here. Okay? So let's do it. So I have here, trying to see it and write at the same time. So looking at this equation, guys, I'm going to plug in what I have out of it, okay? Of course, this part is 0. So I'm going to have m sub A, and that's equal to 5. And then V naught A is equal to 2 plus nothing, really 0, right? So that's just 0. I don't want to deal with it. Equals to m sub A is 5 times 0.866 times V sub A, he gives it to me, is equal to 1, correct? Plus M sub B is 3. I want to make sure, yes, it is 3. And then V sub B cosine beta. See that? Reduce all... Excuse me, I beg your pardon. Okay, sorry. So we have here 5 times 2 is 10. Then I can multiply that and move it to the other side. You see what I'm saying? So that's going to be 5 times 0.866, and that's equal to 4.33 plus 3 VB cosine beta. And then I have 10 minus 4.33, answer 5.67 equals to 3 VB cosine beta, and divide this by 3, answer I get. So basically what I have is VB cosine beta is equal to 1.89, and I'm going to call that equation 2. So now look at this. I have equation 1 and equation 2, and I can solve them simultaneously. You got that? One way to do it, one kind of a cool trick, divide 1 over 2. Divide 1 divided by 2, like this. The reason I do that, look what will happen. VB over VB, yeah, I'm going to do it like this. Let me write it down. VB sine beta equals VB cosine beta equals 0.83 divided by 1.89. You see the trick? So VB's cancel out, and then sine over cosine is tangent. So tangent beta equals to 0.83 divided by 1.89. I'm using my calculator. Answer, and that's equal to 0.439. And therefore beta is equal to, let me take that inverse squared. Let me do it here. Answer equals, I got 23.7. I'm looking at the book and see what kind of answer he got. He got 24. Good enough. All right, I'm sure probably just rounding. So anyway, I got 23.7 degrees for beta. And of course, it should be minus, correct? Because it's below the x-axis. Remember the drawing? Look at the drawing here. It is below the x-axis. That should be a negative answer. He put a negative there. So anyway, if you insist, or you can just say below x-axis. Okay? And then pick 1 or 2. Let's pick 2. I have VB, the one you see right here. See that? That's going to be 1.89 divided by cosine beta. And you just plug it in, and you will get VB. And I'm going to assume that I have done it correctly. He got an answer of 2.1, and I hope we got that, this answer, meter per second. And there we go. You got it? So in this case, VB is equal to 2.1 meter per second. And there we go. We got both of them. Okay? Now, if you can do this problem without looking at the solution, you really understand momentum. Okay? Okay, good. There are two types of momentums. One is called repeat. There are two kinds of collisions, I wanted to say. One is called elastic collision, and the other one called inelastic collision. I want to talk about both of those, and that's about it for that chapter. Right after that, oh, I'm sorry, there is also the concept of impulses. There's only like a page and a half in the book. I'm going to talk about it a little bit. Nothing serious here. But the one I'm going to skip is the center of mass, which is section 8.6, and the section 8.7 is a continuation of it, the motion of the center of mass. And then you get rocket propulsion, which is 8.8. So skip everything after 8.6, okay? And we are now in 8.3, inelastic collision. All right, so let me talk about that. When we say inelastic collision, we mean that when two particles collide with each other, okay, they basically stick together after the collision, okay? I mean, it's not really exactly true, I mean, but for the level of the course of physics that you are taking, that should be good enough, okay? So inelastic for our course is basically the two colliding particles rather, they stick together after collision, and then they move with one common speed. Let me give an example. Well, let me write it down. So inelastic collision means particles stick together AC, okay? Particles stick together after collision. Okay, that's basically what it is. As a consequence of that, what will happen is that the kinetic energy of the two colliding particles is not conserved. What that means is that the sum of the kinetic energy before collision does not equal to the sum of the kinetic energy after collision. I'm going to explain that in a sec. Let me show you a picture. So let's say, for example, I have two cars, train car. What do you call them? Car trains, train cars, like that. Let's say there is a latch here. Train cars, I think that's what it's called. Let's say train car A, and there is another one here, like that. Let's assume both are moving. This is the latch, right? Right here. There is another latch here. Let's say this one initially moving at this speed, V naught A. This one is also moving in the same, we'll call it B here, V naught B, like that. They're both moving in the same direction, except that, let's suppose that V naught A is faster, okay, or larger than V naught B, otherwise it's not going to catch up with it. So we're supposing that V naught A here is greater than V naught B because we want it to collide with it, okay? So this is all BC, okay? So what happens, AC in this case? What's going to happen is that the two trains are two cars. They're going to hit each other, and then they're going to connect like this. Here is A. Here is B. Okay, they're all connected together now. And they're both moving with one single common speed. I'm going to call it big V. Your book uses small v or something else, whatever it is. I like big V for the common speed. Okay, so remember, big V is the common speed. When I say common speed, the speed of both particles after collision when they stick together. Got it? Okay, so let's assume this one has a mass ma and this one has a mass m sub b. So what is the total mass of the object after collision? Well, it's just going to be ma plus m sub b, right? Now, momentum is still conserved. Okay, this is AC. In other words, for elastic or inelastic, momentum is always conserved. You got it? So let me use the conservation of momentum. So what does the conservation of momentum says? Well, it says ma v naught a plus mb v naught b, I hope you're following me here, is equal to after collision. What's going on after collision? Well, there is momentum still, all right. But now the mass, remember momentum is mv, the mass now is this, ma plus mb times the common speed. And that's the classic expression for inelastic collision. This is how it looks like. See that? And then, you know, the problem asks for whatever, you know, let's say it's asking for what is the common speed after collision, or something like that. Okay? Let me see, number 86. I hope it's about, oh, okay, 86. Let's do example 86 very quickly. Next page. Inelastic collision right here. As you can see here, here's a picture. So you have those two gliders, there is Velcro right there, okay, so they are going in the opposite direction, head-on collision that is. Then they stick together, and what will happen, because VA is greater mass maybe, so they both move with one common speed, V sub F he calls it, okay? Where the new momentum here is the mass of A and B together. Got it? Here it is right here. So the momentum of particle A before collision plus momentum of particle B before collision as well, okay, equals to the combined mass, the common mass, whatever you call it, times the common speed, okay? All right, I'm trying to find that example of what I told you about. Here we go. Nope, There it is, right here. Okay, he says, let's begin with a very straightforward collision process. Suppose we perform a collision experiment using Velcro-equipped gliders, okay, in the example 8.4, okay. Glider A has a mass of 0.5 kilogram, and glider B has a 0.4 kilogram right here, okay. Both move with initial velocity, both of them have the same speed, okay. That's 2 and that's -2, okay. Find the final velocity. Basically, he wants to find the common speed, the one I'm telling you about, of the joint, and compare the initial and final kinetic energy of the two. Got it? Okay. Let's see how we do that. I mean, there is really nothing to it except that it's the same as what we have just said here. But let me go over it very quickly. So what I have here, here's glider A moving with velocity 2. The mass of A is 0.5. And then glider B, right here, moving, whoops, it's not lined up, sorry. I'm trying to erase that thing. There we go. So glider B is right here, moving with V naught. This is V naught A, sorry. V naught B is also 2 meters per second in the negative direction. And then M sub B is 0.3, is that right? 0.3 kilogram, this is 0.5 kilogram. And that's BC. And then AC, so they both now moving with this direction. I like to call it big V. Your book uses small v. And he wants to know what is that common velocity. Okay, simple, right? So you just go, sum of the momenta before and after are equal. So that's going to be MA V naught A minus MB V naught B. The minus here because the velocity is going to the left, right? Is equal to MA plus MB times the common velocity, correct? So the common velocity in this case is MA V naught A minus MB V naught B over M sub A plus M sub B, right? You just plug it in now. I think we got everything. So M sub A is 0.5, V naught A, I'm copying from my hard copy here, minus M sub B is 0.3 times M V naught B is 2. I mean, I can put a minus there, but I already took care of it right here, right? Okay, divided by the total mass, and that is 0.5 plus 0.3, okay? And that's it, you just plug it in. So that's going to give you 1 minus 0.6 over 0.8, and you just calculate that. So that's, what is it, 0.4 over 0.8, and that will give me half, it should be. So that should be 0.5 meter per second. So the common, excuse me, for the common velocity is equal to half a meter per second. Got it? Okay. Now he says compare the two kinetic energy. That shouldn't be difficult, right? He says find the final and the joint and compare the initial and final kinetic energies. All right. So we can work on the kinetic energy. That's not difficult. So the kinetic energy of glider A is just 1/2 MA V naught A squared. You can plug in the numbers. You can do it. And you get 1 joule out of it. Kinetic energy of initial glider B, 1/2 M sub B V naught B A squared. And you work it out, and he got 0.6 joule. And then the last one is the kinetic energy of the combined, you know what I mean? So that will be of A and B. I'm going to call it A. Shall I call it A plus B? And that will be equal to 1/2 M sub A plus M sub B common velocity squared. Is that right, guys? And then you just plug in your numbers in there, and he got 0.1 joule. Okay? Now, let me show you something very interesting. Watch this. remember I told you on the top right here, let me show it to you. There, oops, trying to find it, inelastic collision, there it is right here. So what is the characteristics of inelastic collision? Particles stick together after collision, okay, we already know that. And then, as you can see here, the sum of the initial kinetic energy does not equal to the sum of the kinetic energy after collision. Look at that. See, if I take the sum of the kinetic energy before, and they're not equal, I'm just going to go, what is the sum of the kinetic energy before? Well, it's basically the kinetic energy of particle A plus the kinetic energy of particle B, and that's 1 plus 0.6 is equal to 1.6 joule, as you can see here. See that? And then what is the kinetic energy after collision? Well, it's just that, the combined, and it's equal to 0.6, okay? So in other words, there has been a loss of kinetic energy. How much? This delta K is 1.6 minus 0.1, a whopping 1.5 joule loss. Where did it go? Well, it went into something else, say acoustical energy, most of it heat, and so on. In other words, in elastic collision, the energy there, the kinetic energy, is not conserved. The kinetic energy is not conserved, okay? For elastic collision, which we're going to cover in a minute, the sum of the kinetic energy before and after are actually equal to each other, okay? But for inelastic, one of the characteristics of inelastic is that because they stick together after collision, the sum of the kinetic energy before and after are not equal. As a matter of fact, there is a lot of loss of energy, as you can see here. A lot of loss of energy has been just dissipated into some other form of energy, such as heat and acoustical energy. You see what I'm saying? Good. All right, let me move on to elastic collision. Elastic is a little bit more elaborate and a little bit harder, so you want to pay attention. Also, I'm going to give you a couple of formulas that are not in the book that will be very helpful for you to solve problems. Like I said, for this level of the textbook or our course, we only have two types of collision, elastic and inelastic. When we say elastic, it means the two colliding bodies elastically collide with each other, which means they don't stick together. You know, think of it like a 2 billiard balls. You get that? You know, they just, you know, they hit each other and then they rebound, and everything is perfect. You know what I mean? In real life, both situations are kind of extreme, especially the elastic collision, but we're going to ignore that fact. Okay, so elastic collision, basically, the one aspect of it is that particles don't stick together. This is very important. And that is the momentum, same thing. So we still have the momentum before and after are equal in both situations, whether it's elastic or inelastic. The sum of the momentum before equal to the sum. In other words, the conservation of energy is valid for both of them, okay? Hold for both of them. And the second one is that, which is the most significant, is that the sum of the kinetic energy before is equal to the sum of the kinetic energy after. Got it? Okay. And it is best to give you an example and show you how this all works, okay? So I want to start with example 8.9. This is a nice example. Maybe another problem from the back of the book when we start doing problems. So let me go to example 8.9, page 234. I'm going to try to solve it in two different methods, this example. It should be a comprehensive example. Please take notes to it. It's not terribly simple, okay? It may look trivial, but it's not terribly simple. All right, here it is. Elastic collision. It said, let's look at another collision between air track gliders. This time we equip the gliders with the spring bumpers. Okay, these are springs right there, so they will bump, and there will not be any loss of kinetic energy. That's why they do that. All right. As before, glider A has a mass of 0.5, glider B has a mass of 0.3. So we're using the same gliders, and each moves with initial velocity 2, and they approach each other, as you can see here. So they're coming toward each other. Think of it like two billiard balls coming toward each other. What are the velocities of A and B after collision? After collision, okay? How do we do something like that? Okay, I'm going to do it the standard way, and I'm going to show you why it's so difficult, okay? Example 8.9. So what you have in here, here's glider A. Here's the floor, or the track, whatever you call it. Here is B, both moving in the opposite direction. V naught A is 2. V naught B is 2 meters per second as well. And the mass of A is 0.5. I hope you memorized this by now. I have. Mass of B is 0.3 kilogram. This is all BC, right? And then we have AC. Let me write it down below it. And the picture looks something like that. So here is the track. Here is A, moving in the opposite direction. I'm going to call it VA, right? I don't know what it is, Ro. Okay? I have no idea what it is. And then this is B, and it's moving in the opposite direction. Okay? And I don't know that either. Okay? Notice that we have too many unknowns here. I mean, this is the first time we ever deal with, well, we dealt with another problem. But anyway, we have too many unknowns. We have VA and VB. That's what makes it hard. Okay? And I'm going to show you how hard it is. Okay? First, I want you to appreciate, I want to make you appreciate the difficulty of it before I give you the solution to it. All right, so there it is. So I'm going to innocently solve it by applying the rules of conservation of momentum and kinetic energy. So the first rule, sigma P naught equals sigma P. So let's apply the rule of conservation of momentum. Let's apply it. So looking at BC first, we're going to write it down quickly. So that's just going to be MA V naught A plus, or sorry, minus, right? Minus MB V naught B equals to, after collision, which is right here, and that's going to be MA VA. I purposely didn't put a minus sign because I don't know the, let's assume that I don't know the direction. Okay, I'm going to let the mathematics take care of it. I can put the minus sign, it's fine. But if I don't put it, the mathematics will give me an answer of minus. You see what I'm saying? So I'm not going to put it for now. Then plus MB V sub B. Okay, there we go. Now I can plug in numbers. Okay, I can plug in numbers, no problem. But how many unknowns do I have in this one? I have two unknowns. I have V sub B, excuse me, and V sub A. I have one equation, two unknowns. I can't do it. I'm sure you've learned that in algebra. The number of unknowns have to be equal to the number of equations. So I'm kind of stuck with that. So if I do it this way, I'm kind of stuck. I'll just stop here and say, I don't know what to do. I don't know what else to do. Do you see the difficulty of it? So now I can appeal, however, to the conservation of kinetic energy. So I can say, oh, but that's elastic collision. Therefore, the sum of the kinetic energy before equal to the sum of the kinetic energy after, correct? Well, let's see. All right. What's cool about kinetic energy is just you don't worry about direction. So it's going to be 1/2 m sub a v naught a squared. This is the kinetic energy of the first particle, plus the kinetic energy of the second particle, 1/2 m sub b v naught b squared equals to the kinetic energy of the first particle, m a v a squared, second particle, 1/2 m v b b squared. There we go, right? Okay. Everything here is known. Everything here is known. This one, 1/2 ma is known. This is one known. So now I also have one equation with two unknown, VA and VB. So now I can solve these simultaneously, correct? Yes, I mean technically yes, but it is extremely difficult because you get the VA and the VB are squared. You see that? So it becomes really, really hard to solve this equation. I mean, you can try it yourself if you want. I'm not saying it's impossible. You can do it. I've done it before, and you'll get the right answer. But after maybe 2-3 pages of calculation, it's a lot of calculations. Okay? But you have to solve these simultaneously. Solve simultaneously. Okay? But it's tough. Okay? What's cool about it is that your book provides you with an equation, kind of a lifesaver. So rather than doing it this way, there is a quick way of doing that. Okay? So this is the equation that I'm going to give you. You don't need, I mean, if you insist on asking me how did I come up with it, I can explain it to you in a separate lecture. But I'm just going to give it to you, and you accept it. If you want to know how I derived that equation, I can explain that to you later. But here it is. Okay, basically it says the following. Write it down, hang it somewhere, keep it handy whenever you solve elastic collisions. And basically says the following. V01 minus V02 equals to V2 minus V1. Lifesaver. Okay? There is a relationship between those velocities, regardless of the masses. Okay? Famous relation. So what I'm going to do, I'm going to use the momentum conservation. I don't want to use the kinetic opposite. I don't need it, the conservation here for the kinetic. I'm just going to use the momentum conservation, this one right here, and I'm going to use this one to solve this problem. You get that? That's the plan. So let me go back to this equation. I'm going to call it equation 1. Whoops, I think I reached the edge of the screen. Let me go back again, sorry. 1. And this one is equation 2, the lifesaver. Shall we call it lifesaver? That'd be a cool name for it. There we go. Okay, let's go to equation 1 first. Here it is right there. And I'm going to plug in all my numbers in it, all the numbers that I have, okay? All the numbers that I have in that thing. So let's look at equation 1 and plug in all the data. Again, I'm copying it from my hard copy. I hope you have your book on the side as you read the data that is given to us. So M sub A is 0.5 times 2 minus 0.3 times 2. Is that right? Remember, the minus here has to do with it's moving to the left. Now, I'm going to act like, remember, when I use this equation, anything unknown, I'm not going to impose a minus sign or a plus sign on it. I'm just going to act like this is VA. I don't know if it's minus or plus. I don't know. I'm just going to keep it VA, and hopefully the mathematics will take care of that for me. You got that? This is a key idea. Keep that in mind. All right. Especially when it comes to using this equation. So MA is going to be 0.5 times VA. I meant MA. MA is 0.5 times VA. I don't know what VA is. I don't know what direction. Up, down, left, right? I don't know. Just leave it like that. Plus M sub A, M sub B, and that's going to be 0.3 VB. Got it? There it is. Okay, let's clean it up a little bit. What do I get out of that? That's going to give me 1. Half times 2 is 1. Minus 0.3, that's 0.6, equals to 0.5 VA plus 0.3 VB, and then here I have 0.4 equals 0.5 VA plus 0.3 VB. I'm going to box this equation. I'll come back to it in a sec. I'm going to call it equation 1 again, because I got it from equation 1. Now, up to this point, I can't do it. I have one equation, 2 unknowns. Now the lifesaver comes in handy. Now let's use the lifesaver for our problem, Remember, the 1 here is A, and the 2 is B, and the 2 and 1, B and A. You got that? So I'm going to customize this equation for our notation. So the lifesaver equation becomes V naught A minus V naught B equals to VB minus VA. Well, what's V naught A given to us? Right here, 2. And V naught B is also 2. Plug him in. So I have here 2 minus 2. Remember, it is V naught B is also 2 equals to VB minus VA. I know nothing about those two. This is the one I'm trying to find, so I'm not going to impose anything on it. And that gives me what? 4 equals VB minus VA. Now look at that and compare it, or not compare it. Now I can use 2 to solve and 1 to solve for VA and BV. Now this one looks much better than this kinetic energy conservation. You see what I'm saying? It looks much better. I hope you think it's easy now. It becomes really easy. All right, so all you need to do, pick one of them, method of substitution. So let's pick V sub A. So V sub A in this case becomes equal to what? How do I do this? VB minus 4, correct? I'm saying I got the VA from here. Is that right, guys? Now take that and plug into 4. What did I say? I wanted to say 1. So in this case, 1 becomes, this one right here, that's going to become 0.4 equals to 0.5 VA, and VA is equal to what? Let me just fix it. VB minus 4 plus 0.3 V sub B. Clean it up a little bit. 0.5 VB minus 2 plus 0.3 VB, and that's 0.4 here. What does that give me? 0.5, that will be 0.8 VB minus 2 and a 0.4 here, and 0.8 VB equals to 2.4. So VB equals to 2.4 over 0.8. And what is that equal to? Let's see. 2.4 divided by 0.8, answer 3. Okay? So in this case, V sub B equal to 3 meters per second. Isn't that nice? Now, okay, I can go back to this one right here and then plug in VB in it. Let's go back here. VA is equal to VB minus 4, and that's equal to 3 minus 4, that's negative 1. See the minus sign there? Do you see that? Why is there a minus sign? Well, look at the drawing. Let's look at the drawing again. After collision, VA is going to the left. When I was solving, I acted like I don't know. You see, remember? I didn't put a minus sign there. I acted like I don't know which direction. Up or down or left, I have no idea. Well, look at that. The mathematics took care of it and gave it to me. It said, it's to the left. Okay? And B, look at that. There is a plus sign here, right? Which means what? It's moving to the right. And just, in other words, our drawing is correct. Okay? So those are the two answers that I got. Let's see what he got. I hope I didn't make any mistakes, but that's basically what he's asking for. V sub B and V sub A. So he got, next page. I believe he did it the same way. There we go. He has a different version for it. It's right here. It's slightly different from mine. Mine is, I find it easier. But anyway. And he got, there we go. VA is -1 and VB is 3. Got it? Okay, good. The last topic that I want to talk about, and that is impulse. And then we'll do a couple of problems from the homework. Impulse, right here. Don't forget that lifesaver equation. Write it down somewhere, okay? Keep it handy. Where is it? Right here. All right, impulse. Okay, so what is impulse? Impulse is when you exert a force, or when a force is exerted on something for a very, very short period of time. For example, when you kick a soccer ball. Okay, so let's say the soccer ball is sitting on the grass at rest, and then you run towards it, and then you kick the soccer ball. What is the time of contact of your foot with the soccer ball? Well, it's a fraction of a second, correct? So out of a sudden, within that small amount of time, the ball is moving with high velocity, you know, say to the right or whatever, in a certain direction. That's impulse. A baseball bat with the ball. Okay, the time of contact between them is very, very short, and then you get the baseball bat moving to the right, for example. Then the meets the bat, and then now it's moving to the left with very large velocity. Okay. The rifle, you know, when you have a pull the trigger, the bullet is at rest, and out of a sudden the bullet is moving with, the speed of, say, twice the speed of sound or something. So impulse is an interaction or a change in momentum. That's the best way to explain it. Is a change in momentum in a very short period of time. And I like to give it the following definition. Impulse is a sudden change in the direction of momentum. MTM for momentum, okay? Of course, due to what? Due to, I don't like this D, due to a force that acted on an object for a very short period of time. Okay, that's my definition of it. A sudden change in the direction of momentum. Why? Why that sudden change? Because there is a force that acted on the object for a very short time. Short time is important, actually. Okay, I've never seen impulse for a very long time. Short time is very. It's part of the definition of impulse. It's part of the feel for it. It's impulse. Okay. All right. Let me give you an example. Let's play baseball. Okay. So I'm gonna have three situations here. Here is the bat. Okay. And we're gonna assume the bat is not moving, or the speed of the bat is negligible. And then somebody throws the pitcher. I think it's called. Somebody throw the ball toward the bat. Okay, so here is the velocity of the bat, v naught. Excuse me, the velocity of the ball, v naught. The ball has a mass m. Okay, so this is BC. Okay, now there is also DC. What I call DC. These are my own notation. A DC basically is that here is the bat. That time of contact where the ball is momentarily deformed like that, flatten out like here. You see what I'm saying? That's DC. I'll come back to this picture in a second. And then the third one, what I call after the collision AC, you have the bat is here, and then the ball is moving with a velocity v in the opposite direction. Of course, nothing happened about the mass, so I don't need to draw the masses here. I mean to write the masses. They're all the same thing. So the ball didn't lose or gain any mass here. Okay, so those are the three situations. I define impulse. Okay, look at the first and the last, BC and AC. we define impulse. Your book uses the letter J for impulse. That's cool. Okay, we define impulse to be the difference between the final momentum minus the initial momentum. So momentum final minus initial momentum. Okay? Or from our notation, P minus P naught. Okay? Well, let's look at it. Look. We know that momentum is mv. So this is the mass of the ball is m here as well. Again, I'm going to ignore DC for now. Okay, I'll come back to DC in a second. I'm just looking at BC and AC, and that's just a definition. Okay, we define the impulse to be the difference between the two momenta, final momentum and initial momentum. You got that? Okay. So now, momentum is mv. So this means, looking at, remember, momentum is a vector, so the velocity here is going to the right. So the momentum final is mv minus, what is the momentum initial? Well, here it is right here. And that's what? M times minus v, correct? You follow me on that? This minus has nothing to do with the direction of momentum. This minus is the increment, the difference between two things. Delta v, delta p. I mean, impulse is really delta p, if you will. So the delta here is a minus. So in this case, it's going to be mv plus mv naught. It's mv plus v naught. You see that? In other words, it is indeed, impulse is the difference between the two momenta, but most of the time, because of the direction, you actually end up adding the magnitude of the two because of the direction. You got that? You want to be careful about that. When you calculate momentum, always pay attention to the direction. And not all the time, but a lot of times you end up adding them up together, not taking the difference between them. It's very deceiving. Okay? All right, good. Another way of defining it. So that's the first definition. I'll come back to it in a sec. Make it star. Another way of defining impulse. Another way of defining it is to look at DC. Let's look at DC right here, which is the time of contact of the ball with the bat for that very short time, something like 0.15 second, something like 15% of 1 second. What's going on here? Well, what's going on is the following. You have the bat is exerting a force on the ball like that, and the ball is exerting the same force on the bat like that, action-reaction, for a very short time, delta t, okay? It turned out that if I multiply this force with the time of contact, I get exactly this result, the impulse. In other words, impulse J is also equal to F times delta t. Okay? You can pause the video and think about it. But impulse is the product of the force of contact, the contact force of the ball with the bat, or your foot with the soccer ball. You see what I'm saying? Or the golf club with the golf ball. That time of that force that is exerted there, it's a huge force, very, very big force, times the time of contact, which is a really short time, a fraction of a second. Those two together, multiplied, also give you the impulse, and it happens that it's exactly equal to the difference between the two momenta, final and initial. Okay? So those are the two definitions of the impulse. In other words, I can write them in one single equation and say that J is equal to F delta T, or is equal to delta P. And I hope this equation in your book somewhere, got to be there somewhere. there it is, yeah. Equation 815, let me show it to you. I gotta show it to you on print. 814, this is F delta T. Look at that. Look, this is the racket, and this is the tennis ball. Look at that. The tennis ball is instantaneously, or at this instant, it totally deformed, flattened out. Look how flat it is. Because of that huge force the racket is given on it, is exerting on it, and the ball is also exerting on this time of contact is a fraction of a second, and during that time there is this huge impulse is equal to F delta T, the time of contact and the force. Got it? And there it is right here. See that? So F delta T or delta P. Okay? He goes on about those graphs. I mean, you can read about them. I'm not gonna be. They're not terribly important for our course. Okay, good. Let me give you an example. There we go. This is a good example. Simple. So what you have in here, as you can see, you take a ball, you throw it against a brick wall, then it rebounds. So you hit it with a speed of 30 meters per second, the minus here because it's going to the left. And then the ball rebounds with, of course, some of that energy has been absorbed by the ball. It's not an elastic collision. And so the new speed here is 20 meters per second. And he's asking for the impulse, I guess, or whatever it is. He said, okay, so you have to throw a ball of mass 0.4 kilograms. That's a pretty heavy ball. Against a brick wall. It hits the wall moving horizontally with a speed of 30 and rebounds horizontally with a speed of 20, all right? Find the impulse of the force. Find the impulse of the force exerted on the ball by the wall. If the ball is in contact with the wall for 0.01 second, look at the short time. You can't see it, okay? You see what I'm saying? Find the average force on the ball, and so on, okay? So basically, he wants the force and he wants the impulse and the force. Okay, so let's do that. Simple problem. Example 811. Again, I'll just draw a quick picture. Here's the brick wall. Here's the ball moving this way, 30 meters per second. And then you get the ball rebounding 20 meters per second. And so we know the mass of the ball is 0.4 kilogram. He wants the impulse, J. Well, J, we said that at delta P. Remember I told you, most of the time you end up adding the two, final and because of the direction. Not all the time, but most of the time. Okay, so it's going to be P final minus P initial. So that's going to be MV final minus MV initial. I know I'm changing my notation. I hope it's not confusing for you. Of course, this is the V initial and this is the V final here, right? So that's going to be the mass is 0.4. Take it as a common factor. And pay attention to the sign. So this thing is going to the left. That's going to be negative. So that, oh, I'm sorry. I'm starting with the V final. Sorry. And that's going to be 20. So that's going to be 20 right here. Minus, there is a natural minus here because of the increment. And then there is another minus here, right guys? This is another minus here. So that's going to be minus 30. See what I'm saying? And then you just calculate that. So that's going to be 50 times 0.4. 50 times 0.4, answer 20. 20 what? Well, it's a unit of momentum. I forgot to mention what the unit of momentum is. Look, momentum is MV, correct? So the unit-wise, it's kilogram for mass, V meter per second. That's the unit of momentum, okay? Kilogram meter per second. Impulse has the same unit, so kilogram meter per second. Here is the impulse. Okay. Now he said, what is the force? Well, he said the time of contact is 0.01 sec. Okay, so I know that J is equal to what? F delta T. And I just found J to be what? 20 right there. So that's going to be 20 equals F times 0.01. As you can see, the force is very, very large. So divided by 0.01, answer 2,000 Newton. And there we go. Got it? Okay, good. Okay, I am done with what I wanted to talk about. So let me do a couple of problems from the back. Let me just decide on those two. There's so many to choose from. I'll do number 19 first, and then we'll see what's the next one. I'll do. You know what? I'll do 19 and 24. I think that should do it. 19 and 24. I'm going to do. All right. You have 10 problems to work on. Chapter. Oh, I know the problem. I keep forgetting that I know that I can just put in the page number. I just learned about that this semester. Anyway, 19 is on page 250. Right here. Okay, you got this one right here. You have a block attached to a spring. Okay. He said combining conservation law. And by the way, I am very big on conservation law, whether it's conservation of energy and momentum. Please learn this material very well. Expect it on the next exam. Expect it on the final. I'm very, very big on conservation. So you really need to understand physics. One of the fundamental of physics is understanding conservation laws, whether it's momentum conservation or energy. And I like to combine them too. There are a lot of problems in this chapter where you combine conservation of energy with conservation of momentum. Okay. All right. So this one is one of them. And I picked it because I like those kind of problems. Combining conservation law, he said, a 15 kilogram block is attached to a very light horizontal spring of spring constant 500. Okay. And is resting on a frictionless horizontal surface. Suddenly, it's struck by a 3 kilogram stone right there, traveling horizontally at a speed of 8 meters per second. Right there. Okay. Whereupon the stone rebounds at 2 meters per second. So the stone rebounds 2 meters per second horizontally to the left. Okay. Find the maximum distance that the block will compress the spring after the collision. You want to know what is the maximum distance where the block is going to compress the spring. Okay, so how do we do this problem? Well, let's talk about it. Again, always draw. Always draw. Okay, you're not reading history or something. Always make a diagram. It will really help your brain to think about it. So here's what I have. So far, I haven't even thought about this problem. I read it. I assigned it a long time ago, but I've never done it. So I'm about to do it now. So the way I do it is I'm just going to draw it, and hopefully, I am hoping, the idea of how to solve it will come to my mind. So go back to the picture. I'm looking at the picture for my hard copy. So here we have the mass. The small mass is 5 kilogram. The velocity here is 8 meters per second. And the mass of the block is 15 kilogram. We call the block 2, and this one is 1. I like to give them names so I can distinguish the two from each other. There we go. That's what we have so far. This is V01 in this case. He says that the block is compressed. So let me draw the picture again. So now, here is how it started, right? So now what happens is that the spring is compressed. The block now is here. It's compressed the distance x here. Maybe I should put it here. Sorry, I'll put it here. And then later on, what happens the block is moving with another velocity and u speed of 2 meters per second. That's what he said. Okay? So if I look at it again, he says, let me go back. Okay, the spring constant 500, 3 kilogram. Find the maximum distance that the block will compress the spring. So I want to know x value. Okay. So this is a value of k, where k here is what? Is 500 Newton per meter. Okay. So how do I do a problem like that? Well, since I am talking, there are several ways of doing it. The one, since we're doing momentum in this chapter, I'm just going to use the concept of momentum. So momentum is always conserved, whether it's elastic or inelastic. So I'm just going to go, all right. So in this case, the sum of the momenta before is equal to the sum of the momenta after. Okay. So what's going on before? Well, it was only the stone, M1 is moving, right? This is that one right here. So in this case, it's going to be M1 V01, right? After collision, what happens after collision? Well, what happened is that the moment the stone, let me take the case where the moment the stone is moving the block. So when the stone comes to the block here and rebounds, so what's going to happen is that the stone is rebounding this way. This is V1, and while the block is moving this way, I'm going to call that V2. You see what I'm saying? That's what's happening here. So in this case, I will have oh, I know. I'm sorry. I think I drew the wrong picture. I wanted to draw a stone here, not a block. That's pretty confusing. Can you please delete that? Sorry about that. I'll come back to the third picture in a second. But let me repeat again. I hope I didn't confuse anyone. Okay, so we have the stone coming. Okay, now the stone hits the block. The moment it hits it, it rebounds with a speed of 2, right here. Okay, and then the block moves in this direction with a speed V2. I don't know that speed, do I? I don't know that speed. So what I want to do, I want to use conservation of momentum for that to find V2. I'll tell you in a minute why I want that V2. Okay? So the momentum before collision is just basically the momentum of the stone. After collision, well, it is the momentum of the stone backward rebounding and the momentum of the block going this way, correct? All right, so that's going to be minus M1 V1 plus M2 V2, right? Because the stone is going to the left. Now, put in all my numbers and hopefully be able to solve for V2, which I think I could. Let's do it. So I have here M1 for the mass of the, I forgot what it is, 5 kilogram. Right here, and this one is 15 kilogram. So, all right. So I have here 5 kilograms times the velocity of the stone is equal to 8 equals minus 5, 2. Correct? With the minus is already taken care of, right? Plus the block is 15 times V2. See that? So now I can use that to this equation to find the value of V2. So that's going to be 40 plus 10 equals 15 V2. I'm doing algebra in my head. I hope you're catching up with me. So V2 is equal to 50 over 15. Did I make a mistake here? 50 over 15. I'm not matching the answer that I have here. I'm sorry. You're probably screaming at me. You probably know what the mistake is. I know there is a mistake somewhere. 5 times 8 is 40, right here, equals to 5 times, he said 2, right? Yeah, 2. And that's going to be that. That's going to be minus 10. You move it over here, it's going to become a 50. And that's 15. The mass is 15 kilogram. It's 15 kilogram, all right? And so therefore V2 is is equal to, so 50 divided by 15, I get 3.33 meter per second. Okay, you know what I discovered? I think in the problem in the book, the mass here is 3 kilogram, not 5 kilogram, I think. Yep, 3 kilogram. So anyway, it doesn't matter. I put it, mistakenly, I put it 5. So anyway, that's why I'm getting a weird answer. Anyway, so we have that. There we go. So we have V2. Let's just assume it's 5 kilogram. There we go. I got V2. Now, what do I need this for? Okay, let's think about energy now. Pay attention. So the stone hits the block. Now the block is moving this way. In other words, when the stone hits the block, it gives it kinetic energy. What happens to this kinetic energy? Or what does the block does with the kinetic energy? What it does, it's moved to the right and eventually will stop, which means all that kinetic energy has been converted into compression energy to compress the spring. In other words, this kinetic has been converted into stored energy. Okay? Stored energy. So in other words, all the kinetic energy, gained by the block has been converted into stored or spring potential energy. Energy, my pen is not working well now. I'm trying to erase that thing. Hold on. There we go. Okay, what that means is that the kinetic energy gained by the block, which is 1/2 m the block to v2 squared, has been converted into 1/2 kx squared. Remember the 1/2 kx squared? This is the stored energy in the spring. He's asking for x. How much compression? This compression right here. Well, here it is. I can just solve for x. So the halves cancel out. You solve for x, and it turned out to be m2 over k v2 squared under the square root. And then you just plug in your numbers, right? So x equal, of course, I am using a different mass, so that's kind of messed up the whole thing. But anyway, so m2, which is the mass of the block, is 15, divided by the stiffness constant is 500, times v0 is 3.33. I don't know what the actual answer is, to the power of 1/2, and then you will get the compression. You got that? That's basically what he's asking for. Okay, good. Okay, the next problem that I want to do is number 24. And like I said in the past, I need to keep the video below 2 hours, otherwise the system will not allow me to upload it. And that in such case, I have to start cutting the video to make it below 2 hours, which I don't want to do that. So I'll try to, I'm hoping I'll finish before, right now it's 1 hour and 43 minutes, so let's hope I'll be able to do it in less than 20 minutes, which I think I will, I hope. Anyway, problem number 24. Let's look at it. It's on page, same page. Right here. He says a 5-gram bullet is fired horizontally into 1.2 kilogram wooden block resting on a horizontal surface. The coefficient of kinetic friction between the block and the surface is 0.2. Okay. The bullet remains embedded in the block, which is observed to slide 0.23 meters along the surface before stopping. Okay, this is not a trivial problem. What was the initial speed of the bullet? Okay, now there's a similar example in the book. I have not covered it just for the lack of time, but I urge you to read it and let me know if you don't understand anything. Let me just point it out to you before I move on this problem. It's example 8.7. Okay, page 231. It's called the Ballistic Pendulum. It's a very, very nice example. Similar to it, similar to this problem. So you may want to take the time to read that problem, to read this example. Okay. So what you have, here is the story. The story is the following. By the way, this is an old way of calculating how to find the speed of a bullet. Anyway, so we have a bullet here with some velocity we don't know. The mass of this bullet is 5 grams, mass M1. Here is a big wooden block just sitting there, but the surface is not frictionless. It is actually rough surface. The mass of the block is 1.2 kilogram. Okay, that's all BC. Okay, this is all BC. What happens then, AC, is that the bullet comes to the block, penetrates through the block, becomes embedded into the block, causes the block to move. Basically what happens, here is where the block is initially, correct? So now the AC is that the block is here, here's the block, the bullet is embedded in there, made a hole there, but we're ignoring the hole, right? And it has moved the distance x. And we are saying that there is friction here. We are taking the friction into consideration. Okay? Now he's asking the question. This is AC. The eraser doesn't work anymore. Bear with me. It's not working. Maybe I need to restart the computer. Okay. He said the bullet remains embedded in the block, which is observed to be 0.3 meters along the surface. What is the initial velocity? Okay, so he gives you x here. So basically, here's the data. X here is 0.23 meters, and that's about it, really. That's all we know. Oh, and he said the mu value, the kinetic friction, the coefficient of kinetic friction is 0.2. He wants to know what is V naught, okay? Now, I want to use conservation of momentum. This is an example of inelastic collision, correct? Because they kind of stick together after collision and so on. But here is the trick. Again, this has to do with the ballistic pendulum and that example that I pointed out for you. What I want to do is to say, see, right before the bullet what do you call it, become embedded or combines with the block. In other words, right before that. In other words, when the bullet is right here, watch, here I am right here on the, when the bullet is right here. Okay, just at the moment it penetrates the block, and that means at this stage right here, what's happening, you have both the bullet and the block system are moving with one common velocity, big V. Okay, this is where, so in other words, I want to calculate the conservation of momentum between the bullet before collision, BC, and the moment the bullet becomes right embedded right here into the block, and now both of them are moving with one common velocity. Okay, right at that moment. Okay, it's a trick that you need to learn how to solve it. So anyway, so we go, okay, sum of the momentum before equals sum of the momentum after. So in this case, M1 V naught 1. Of course, the momentum of the block is 0 because initially it's not moving. Now after that, after collision, you have the mass of the block, mass of the bullet plus mass of the block times that common speed that I'm not interested in, but it is there. Okay, so I have this equation. Okay, so I'm going to box this equation. I'll come back to it. Remember, I don't want this big V. I am not interested in it. Okay, but it's there. I'm kind of stuck with it. What I'm interested in really is the velocity of the bullet right here. This one. This is what he's asking me for. So this is the best thing I could get out of the momentum. Okay, so what's another thing I can do? Well, conservation of energy. Now look at this. Let's go back to the bullet when it's right at the moment it enters the block. what happens, the black bullet system has a kinetic energy. This kinetic energy will cause it to slide on this friction surface until it's stopped. Correct? In other words, there has been a work done by the friction force. That friction force, or the work done by the friction force, is equal to the initial kinetic energy. In other words, 1/2, use conservation of energy here, 1/2 m1 plus m2 of the kinetic energy of the bullet block system is equal to the work done by friction. Which is what is the work done by a friction or a force? It is Fx. F is a friction force. Okay? And what is F equal to? Well, it is mu n, the normal. Well, what is the normal here? The normal is nothing but the weight of the black bullet system, right? So that's equal to mu, kinetic mu, times m1 plus m2 g. Now put it back in here. So I have here 1/2 m1 plus m2. That's eraser. There we go. V squared is equal to mu sub k m1 plus m2 gx. Look at that. Those two cancel out. I can solve for v, the big V, that is. And that's equal to 2 mu sub k gx under the root. Now, why do I solve for v, the big V, even though I'm not interested in it? Well, that's exactly my point. I'm not interested in it. I'm going to go back to my momentum equation and plug this thing here right there and solve for v naught 1, and I'm done. Okay? So back to the momentum equation. Call this star. So plug into star. Star says what? Here it is. mv naught, m1 v naught 1 equals m1 plus m2 times big V. Now plug it in, or let me just solve for v naught 1 first. That's going to be m1 plus m2 over m1 times v, or m1 plus m2 over m1 times the square root of 2 mu sub k gx. And there we go. I have an expression. I agree with you. This is not an easy problem. That's why I want to do it. There we go. And we just plug in the numbers. You can do the numbers. And whatever answer you get. Okay? So the hard part about this problem is to see that this kinetic energy here, that is the moment the bullet enters the block, so the black bullet system have gained kinetic energy. That kinetic energy converted into work to move the block all the way to a certain distance right here, Well, it has done work, Fx, F here being the force, the friction force, x. You see what I'm saying? That Fx is equal to the original kinetic energy. That's what I've done here. Right here. So the kinetic energy is equal to the work done by the friction force. That's probably I think this is the hardest part. If you can see that, then you're done with the problem. And then you just work it out. Okay? Okay, I am going to stop here. I hope this is beneficial. And have a good week.